effect in organic chemistry. So what is steric effect? So basically, sometimes due to the bulkiness of some group, the disposition of atom takes place in a molecule. This is called the steric effect. I will take few examples here to explain the steric effect. So let's say the example 1. There is two amine. One is N-dimethyl aniline and another one is 2 extra methyl group at ortho position of N-dimethyl aniline. Now, if we give this electrophile, then a diazo coupling reaction will take place. So, what will happen? This will attack at the para position in such a way, and a diazo coupling reaction will take place. But if 2 methyl group are introduced at the ortho position, then what will happen? Then this, due to this 2 methyl group at ortho position, the rotation will take place with this CN bond, and this 2 methyl group will feel some steric hindrance. Due to this, the rotation will take place with along with the CN bond, and it will rotate somewhere, and the 1 methyl group will go above the plane and the other methyl group will go below the plane to that plane of the benzene ring. So rotation will take place in this bond. Now, if it happens, then this lone pair of electron of nitrogen cannot come into resonance with this benzene ring because those are not in the same plane. So this is called steric inhibition of resonance, SIR. So due to this, coupling will not take place for this amine. So this is one example of steric inhibition of resonance. So next, if we see, the next example is the SN1 rate. If we take that, these halides we have taken, this is tertiary halide, this is secondary, this is quaternary, this is tertiary, this is secondary, this is 2 degree, yes, this is secondary, this is tertiary, this is 1 degree, primary. So here CH3 group, we had increased number of methyl group in that right to left to right, right to left. Now, as you know that if you see my previous videos in SN1 reaction, I had already explained everything regarding the mechanism, solvent effect, steric effect, and all these things. So, if you see that on increasing the methyl group, the carbocation stability will increase, so the rate of SN1 reaction will increase. But if we consider the SN2, it will be the reverse. If we consider the SN2, then the rate will be reverse, because as the number of methyl group will increase, there will be steric crowding with this carbon, which will cause that molecule less rate for SN1 reaction. Like, you can think like that. So this will be the disposition of these three methyl group. So here these three bulky groups are there, and due to this the nucleophile cannot attack from this back end to displace this bromine in the halide. So SN2 reaction will take place for this 3-degree tertiary halide. So this is also one example of steric. The next will take place will come to the Friedel-Crafts reaction. So this is one tertiary butyl group, tertiary butyl benzene. If Cl2 FeCl3, as you all know, that this will produce Cl plus electrophile. So this electrophile can come to either at ortho position or in para position. But due to this tertiary butyl group at ortho position, there is less probability to come the Cl at ortho position. So it will come. So substitution will take place. Electrophilic substitution will take place at the para position. The major product will be the para one. So this is another example of steric. Another example of steric ingredients. So next will come to the trend of nucleophile. So we had taken 1, 2, 3, 4 nucleophiles. What will be the what will be the strongest nucleophile? So as you see, if we increase the number of methyl group from left to right, then the bulkiness will also increase. This is the bulkiest one. This is least bulky. This is small. So as the bulkiness will increase, so it will be difficult to act as a nucleophile. It can act as a strong base, but it will be weak nucleophile. So the nucleophilicity trend will be like this, and due to the steric hindrance, it will be the trend will be, it will be next less nucleophile. Next will come to another one, the acidity of this 3 benzene ring. Benzoic acid, substituted benzoic acid. So one is orthomethoxybenzoic acid, paramethoxybenzoic acid, and the benzoic acid. So you can see that we can explain this with the help of the stability of the conjugate base. So this is the conjugate base. So this is the conjugate base. Now the stability so it will have equivalent resonating structure. So it can come here. That's why the negative charge at carboxylate ion will be equally distributed between these 2 oxygen. So the resonance hybrid will be O, this is minus half. Now here one thing, the benzene ring also come into resonance with this carboxylate anion, carboxyl group, because If the whole thing is in the same plane, then the pi electron cloud of the benzene ring can come into conjugation with the carboxylic group, carboxyl group. So that's why due to the if there is a CH3 group, the benzoic acid will be less acidic than acetic acid. And also there is minus I effect of the benzene ring, but that is quite lesser than the plus R effect. So due to this, now if one methoxy group is introduced at the ortho position, then what will happen? The rotation will take place between this carbon-carbon bond. And if the rotation will take place, then it will move from that plane of the benzene ring, move out of the plane of the benzene ring. And that's why then the benzene ring cannot come into resonance with this carboxylic acid group. And that's why then if it come into resonance with the carboxylic acid group, then there will be less possibility of this negative charge to be delocalized. And as due to the presence of methoxy group, and the rotation of CC bond, it will move out of the plane. So benzene ring cannot exhibit the plus R effect. And that's why it is more stable. That is the orthomethoxy group, orthomethoxy carboxylate is more stable. Benzoate, orthomethoxy benzoate. So this will have stronger acidity than the benzoic acid. If we consider between the benzoic acid and the para, then in para it will show the plus R effect and it will decrease the acidity than the benzoic acid, because that orthomethoxy group will show the plus R effect, and this will reduce. This is COOH. This will reduce the conjugation of the carboxylate anion, and that's why the acidity will be less. So that the nature of the acidity will be like this. So guys, if you have any doubt regarding this video, regarding this study concept, please let me know. Thank you. Have a good day.